Hello everyone, in this episode of What the Fast, we continue our look at aero. Now, in our first episode about aero, we discussed some basic principles and took a look at the front end of the car. In this episode, we're going to take a look at the aero at the back end of a car. But first up, I want to take a quick little look at the side skirts. Much of the information and the work on Jet 200 in this feature are part of an AMB Aero Best Practices package. These packages start from as little as $2,000. Andrew Brilliant has let us release this information to help our viewers make better informed choices on aero parts, avoiding counterfeit and ones that don't work, plus better understand aero. AMB Aero will be releasing more video features in the future on specific topics and aero parts. Now, when it comes to the side skirts and the design of the side of the car, it can get very complicated and realistically needs to be designed by an aerodynamicist with CFD and all integrated into the car. But from an enthusiast point of view, if you want to dumb it right down, when it comes to side skirts, the easiest way to think about it is you want them to do two jobs. The first and easiest job is to stop air from getting under the car. And most basic side skirts will help do that. Usually they leak around the front a little bit though, but essentially you're stopping air from coming into the side and getting under the car, which obviously creates lift on the car, which you don't want. And the other option you can do if you modify your side skirts like we have is essentially we've got a fence that sits along the bottom, helping air stop it from going under, but we've also created essentially an air guide that is trying to essentially force air out from under the car. The less air we have under the car means the air that is there has to travel faster to fill up that void, get a bit of low pressure, but also means the less air that's under there means the less turbulence and the less work it's doing, because we don't have a flat floor, so essentially we don't want any air underneath the car, because any air under the car is just hitting the underneath of the car and becoming turbulent, creating drag. So side skirt, two things: stop air from getting underneath, or secondly, also help get air out from underneath the car. So the thing that most people think of when you talk about aero is wings and spoilers at the back of the car, but they are just so misunderstood. First up, let's talk about the difference between the two. A wing and a spoiler are not the same thing. Now, a wing is exactly as it sounds. Think of it as something that is separate to the car that sits in its own airstream, and it is an aerofoil the same way as a wing on a plane, except it's upside down and the force goes down. And obviously it transfers that downforce through these uprights down into the chassis, pushes down on the car. Now, a spoiler is attached to the car like this boot lip spoiler that we have along here, and essentially it has a totally different job. Its job is to spoil the air as it comes over the car, hence why it's called a spoiler. And what it's doing is it's actually spoiling the lift that is created naturally over the top of a car due to its shape. So let's look at that again. Now, last video we talked about how we have an aeroplane wing like this. Air comes over the top, air goes underneath, air over the top goes faster, so you have a low pressure, high pressure, you get lift. Now, the shape of a car is also naturally like that as well. If you just look at it as an overall thing, air over the top has to speed up as it goes over the top, and you get a low pressure zone over the top of the car, over the roof. Now, essentially what a spoiler is trying to do is help try and reduce that, but yet it's doing it from back here. All right, so let's look at the air flowing in two different parts of the back half of the car. The air that flows over the roof, as it comes over the back of the roof onto the windscreen, it'll often break away like this and create some turbulence over the back of the windscreen as the rest of the air tries to go like that. Basically, that separation point is all based on the angle of the roof and how smooth it is, etc. In some ways, it's a good thing, because if the air was able to flow over there smoothly, it would actually help create more of a low pressure in the top of the roof. But obviously, all of this turbulence creates drag, i.e. helps slow the car down. So that's the first thing you have to worry about, is the flow over the roof. But the most important thing we want to look at, and we'll come back to why that's important later, is the flow over the boot lid. So as it comes off the back of the car, it just breaks away and becomes turbulent. In fact, you'll often get reverse flow back towards the back of the car. So all this turbulent air over the back here creates drag, creates a low pressure zone behind the car. Every car has a low pressure zone behind it, which you can use to your advantage, but the low pressure zone actually creeps back up over the boot lid and creates a low pressure zone above the boot. You've got high pressure down here, you've got a low pressure here. What does it do? The back end actually lifts. We've seen GTR owners remove their rear wing completely, go to the drag strip, and they come back and they go, wow, the car was mega unstable in the back end, because essentially they're now getting rear end lift by not having any type of spoiler or rear wing on the back. So how does the spoiler work? So I'm going to draw a large spoiler on the back of the boot lid here. I'm going to exaggerate it a little bit so it's easier to see. But essentially what happens now is the air that flows down here, even the turbulent air that comes off the back of the roof, flows down over the boot, hits this spoiler, and now you can imagine comes out more like this. So now this turbulent area is forced to move away from the car more and detach away from the car so it doesn't create as much drag on the car. You're moving the turbulence away from the back end. But the other thing is now the low pressure that's here can't find its way back up over the boot lid. So you're not getting a low pressure zone over the boot lid anymore from that. Your low pressure zone is staying behind the car and even moving back. So as you move this low pressure zone back, it can do more work to help actually suck air out from under the car. And obviously doing that is going to help any aero devices you have under the car do their job better, and also help draw air out from under the car smoother and be less turbulent back here and less drag. So the spoiler actually has two areas where it works. One is back behind the car, but the bit we're going to look at here is as it hits here, what happens is you get this big turbulent area here, a high pressure zone, but it also backs it up and creates kind of like a stagnant layer of air here. So two things have happened now. All of the air hitting the spoiler creates a high pressure zone. Now obviously like a NASCAR with a big tall spoiler actually creates quite a fair bit of high pressure just from hitting the spoiler alone. You can see on a big spoiler, all that red high pressure zone across the spoiler, huge high pressure zone, but what we're looking at that's also important is all this sort of stagnant air it creates here. It kind of becomes a pocket of trapped air between the window and the spoiler. That kind of acts like a different bit of bodywork for the rest of the air. So the rest of the air is now kind of coming over and flowing over that nicer. That sort of trapped pocket makes the rest of the air flow nicer, which is less drag. Now, on our car, and even on an R32 GTR, when you see the N1 boot lip spoiler, having that little spoiler on the back there not only stops the low pressure zone from not being able to get there, it helps smooth out the airflow. But if you can imagine this, if you've now got a wing here like this, sitting in that airflow, now that we have a lot smoother airflow coming off the roof of the car, your wing will actually work better. So when we did the wing on Jet 200, Andrew Brilliant told us what size, what angle boot lip spoiler we should put on there to actually increase the efficiency of the wing. So really, it's quite a simple concept when you look at it from the perspective of this trapped pocket of air essentially kind of moves the bodywork up and makes it smoother. So now all the air off the roof, it flows smoother. You've got smoother air to the wing, so the wing works better, and you've got less drag because all of the airflow is staying attached. So a little boot lip spoiler can actually do a lot more than you think. Now the thing about boot lip spoilers, you see them on a lot of performance cars to help tidy up the drag in the rear end. A little tiny boot lip spoiler on an M5, for example, can have 50 kilos of downforce at over 200 k's an hour. They can actually create downforce even when they're very small, or obviously just help with the efficiency overall of the rear wing. So a spoiler does a lot of things. They're pretty cool. All right, so I'll use a real world example of where a manufacturer has added a little spoiler to help make their wing work better. Let's look at a GTR, shall we? Why? Well, we've got one. That's the rough shape, but if you look at the actual shape of the rear wing, we'll just sort of like highlight the blade shape at the top. They've actually got a pretty good aerofoil on them. But here's the thing. So the air coming off the boot, as it separates, gets kind of turbulent like this. Now, the good airstream that's not turbulent may not be coming down far enough to work effectively on the rear wing. So what Nissan did is they added the N1 boot lip spoiler like this under the wing, and we talked about this earlier, that it essentially created like this stagnant air pocket across the boot. So now more of the air coming down is staying attached and smoother. So now that wing gets fresher air and the wing is more effective. So the boot lip spoiler isn't just about stopping the low pressure creeping back up over the boot. They added the N1 boot lip spoiler to make the rear wing more effective. Now, essentially, Nismo designed and added that wing for Group A racing. Obviously, they're restricted by regulations and how big it can be, etc. But just that little boot lip spoiler, that's how that worked and why it was developed for the GTR. All right, now let's talk about wings on a car. Now, to be honest with you, a lot of wings that you see on road cars are massively confined by space, crash regulations, pedestrian regulations, etc. So it's only so big that they can be. But when you start looking at race cars, that's when you see how serious wings can get. If you look at the Pro Class built in Time Attack, they have triple element wings that are over 2 meters wide, over 1 meter long. They are massive. They can generate over a ton of downforce just from a wing. But then on a road car, some wings are just purely decorative. So they really can be from, a ton of downforce to nothing and anywhere in between. In fact, a lot of aftermarket spoilers probably don't even create any downforce, they just create drag. So when you buy a wing for a car that you actually want it to improve the performance of the car, it's important that you buy one that's actually been CFD designed, wind tunnel tested, etc. So you actually have some data. For example, we have an APR 1000 wing on our 200SX Jet 200. That wing was designed by Andrew Brilliant, CFD tested and designed, so we know it works. We know the data, we know exactly how much downforce we can get, we know how to set it up. So all that data actually exists. So for motorsport use, that's what you want to go for. If you just want it to look pretty, hey, do what you want. So let's talk about a little bit of theory of a wing first, so to help you guys kind of understand what you're looking at on some of these race cars. So here's a normal aeroplane wing. Everything from an aeroplane wing to a car wing, just think of it as upside down. So we talked about how air comes over the top, like this, comes around the bottom, and because the top has to go faster, creates a low pressure, high pressure, creates lift. We also get the secondary effect of air just basically hitting it, bouncing off it and creating a force that way, and the opposite of that force bouncing, the air bounces off, is also some more lift. So now I want to talk about with a wing is how the airflow changes based on the angle of the wing to the air. Now essentially, to measure what's called angle of attack, you need to have the chord line. Now a chord line is taken from the trailing edge tip to the center of the leading edge, and it's just a straight line from there to there, like this. Now notice the curve of the aerofoil is like this, but when you're talking about angle of attack, you just take that chord line. So from the center of the curve to the trailing edge tip, that is the angle reference you're going to use for the airflow. So let's bring some airflow in. And basically this angle here is your angle of attack. Why is this relevant that you need to know what angle of attack is? Well, for what we're going to talk about next. Okay, so we're going to get a wing that's not got a lot of angle of attack versus one that has a lot of angle of attack. Air's going to hit this, flow around it nicely, and work efficiently. Basically, the layer of air going over the top stays attached. And when I say it stays attached, I mean it has a smooth airflow over the top of the wing like this. Now, if you get a high angle of attack, what happens is, as the air comes over the top, it can't flow smoothly down the back edge, and it breaks away like this. And then you have all this turbulence behind the wing. So the air comes over, can't stay attached, breaks away, until you get to a layer up here that stays attached. So when the air breaks away like this and becomes turbulent, obviously the wing just stops working. And basically, well, it's called a stall. You've heard about aeroplanes, they stall and fall out of the sky. That can also happen on a plane wing, but obviously on the car, it's the other way around. It's like this. And it's trying to create downforce. But if that air breaks away and stalls, the wing stops working. Why is this important for a car wing? Well, it lets you know that there's only so much angle you can put on the wing before it stalls and just doesn't work anymore. You know when you see guys with their WRX with an adjustable wing and they flip it right up? It's probably stalled and doing nothing. However, I will say this, a stalled wing can still make downforce. Now, if you just had a steel plate like this on the back of a car and air just hits it dead on, well, that air has to bounce up that way. And the opposite of that, obviously, is it pushes down on the back of the car. So even a stalled wing can create downforce, but just remember, behind it is all this turbulent airflow creating drag. So a stalled wing can still create downforce, but it's not going to create as much downforce as a wing that isn't stalled, and obviously the stalled wing will have a whole bunch of turbulence behind it. So for people out there that go, oh, I've got my wing on a crazy angle and I've still got more downforce, well, yeah, you do, but you also got a bunch of drag and it's not as efficient as it could be. Now, where does a wing stall? Well, each one's different. Some stall as early as 15 degrees, some can go to 20, 25 degrees. Depends on the shape of the aerofoil, depends on whether there's multiple elements to the aerofoil. There are so many variables that we could sit here for the next 10 years talking about it. In fact, aerodynamicists spend their whole life still learning about how to make more efficient wings and aerofoils. So if you've ever flown in a passenger airliner or watched movies and you've heard about them putting the flaps down for takeoff and landing, you would have noticed that the wing actually changes shape. So there's a normal aerofoil, but there's a little section at the back of the wing here that's like another little aerofoil, and it comes back out and sits like this. So that's basically a slotted flap. Now what does that do? Well, let's just say we've got some more angle of attack hitting the wing and it flows over. It would normally want to separate back here and break away, but some of the air hitting underneath the wing will then be forced to go up through that slot and help keep the air attached. So this whole theory of how a flap works on an aeroplane wing is exactly the same as when you see a multi-element wing on a car. Now you can have one flap like that. Some of them on big airliners even have another one that comes down and have essentially another one. So more air can flow in through here and keep that boundary layer attached and keep the wing nice and efficient. Now, here's another thing you need to consider when it comes to a multi-element wing. We talked before about the chord line being from here to here. Well, on these wings, the chord line is actually from here to here. So the chord line of the wing is now actually outside of the wing. How is that relevant? Why is that relevant? And how do we show that in real life? Well, let's have a look at Jet 200. If we had a single element wing, we would probably have a little bit more angle than we do now. It's only a very light angle on the actual main element of the wing, probably only 5 degrees in terms of angle of attack. But if you have a look at the second element, and you can see the little slot through here where air comes through, just like we showed here on the flaps of an aeroplane wing, this bit is at a very aggressive angle, past 45 degrees. But the actual overall angle of attack of the wing, if we go from the front tip of the wing to the back leading edge of the second element, that's how much angle we actually have. It's actually more like 20 degrees in total of angle of attack. So the main bit looks like it's not deflected much, but this bit is quite a lot. But just remember, without that gap through here, that probably wouldn't work. So when you see a really aggressive aerofoil and it's flipped right up and hasn't got that second element, it's probably too aggressive and not working. Another example of that is I notice a lot of is when people add a wing extension to the back of an R32 GTR wing, the Rocket Dancer, that hasn't got a slot in there, it's just a big extension. So if you can imagine from the tip to the tip, it's now got a huge angle on it. So what's it gonna do? It's just gonna stall, makes the wing not work, just adds drag. Looks pretty, but doesn't work. So a true multi-element wing, that's why it looks like it's on a big angle. This second element is just purely because now the overall angle of attack is from this point at the front of the leading edge of the main wing to the trailing edge of the second element. So essentially what a multi-element wing allows you to do is have some pretty hectic angle of attack overall without stalling the aerofoil. So here's one at a normal sort of angle, air comes over, stays attached, doesn't stall. This one hits, comes over and stalls, so that airfoil doesn't work. But this one, if you have a look at the chord line here and the chord line here, this one looks more aggressive but still has less overall angle of attack. But as we said before, air can come over the top, comes through the slots in here and keeps the airflow nice and attached. So a multi-element wing basically can be more aggressive to create more downforce, but at the same time, the air stays attached so you don't get the drag. So as you can see, wings, there's a lot to them and a lot of aerodynamic science behind them as well. So we could sit here for hours talking about them, but that is the basics. Another thing to talk about on rear wings is end plates. Now these end plates work in the same way that the winglets work on an airliner, such as a Boeing 737. If you can imagine that the air coming underneath the wing has this low pressure, it actually wants to spill around the side into the high pressure. As it spills around, it actually then creates a vortex or a vortice. Now aircraft want to minimise that for the same reason these cars do. If the vortices are too strong, it can actually create drag. So these end plates essentially move the vortice back behind the wing and behind the car. Because as this low pressure comes out from behind the wing and meets the high pressure, they don't actually meet until after the wing, helping keep the lift over the aerofoil. But as they sort of mix further out, the vortice comes out behind the car and isn't attached to the car. So they stop, basically they're stopping leakage of lift around the side of the aerofoil. So these end plates, they're not decorative, they're actually very important for helping make the wing work better. So this last part's probably going to upset a lot of people, and that is talking about rear diffusers. Now, first up, if you've bought a rear diffuser off eBay or some Japanese or Chinese website that makes rear diffusers for your car, I'm telling you right now, 99.999999% of them just don't work. All they do is add drag. Purely cosmetic. Manufacturers make diffuser-looking panels on the back of their car. Same deal. They are just cosmetic. They look good. The type of cars that have a real diffuser on the back are your supercars, your exotics, because you need a flat floor to make a diffuser work. Now, first up, a rear diffuser, let's look at the shape of it. Shaped like a wing, right? But on cars that have a flat floor, the air that's nice and smooth under the car from the flat floor does this. Think of that, upside down wing. Now we get downforce. It also helps move some of that turbulent air behind the car further away. Now, earlier we talked about creating a low pressure here behind the car. Well, the more you move that low pressure back, the more it actually helps suck air out from under the car. So the more you control that low pressure behind the car, the more effective your diffuser is. Now, if you have a look at the car with a flat floor, you've got smooth air that hits the leading edge of the diffuser and then do that. Now, time attack cars we mentioned in our last video have giant tunnels underneath. They kind of work like this, except they're massive and they sometimes come out halfway through the rear bumper or higher, and they just become massive, essentially massive rear diffusers. So why don't they work when you don't have a flat floor? Well, you know that you've got, a differential under here behind your wheels, and you've got a gearbox up under here, and you've got a tail shaft, and you've got all this stuff under the car. And the air under the car isn't smooth. It's actually just doing this. It's all turbulent air. Now, turbulent air creates drag, and turbulent air doesn't work on a wing. So when this turbulent air hits the wing, it's just more turbulent air going everywhere. And that's it. That's why your rear diffuser doesn't work. There are instances where they can work though, but generally that requires CFD modeling, where someone like Andrew Brilliant will look at the underside of a car and kind of work out where in the airstream you could put that rear diffuser so that it actually will have an effect. Andrew Brilliant said that sometimes at the racetrack he would see an Evo or Rexy or whatever spin off the track, tear their rear bar off, and they'd go out and they'd run a PB. And they'd come back, yeah, PB, put their rear bar back on, and then go slower, and they couldn't work out why. And I'll tell you why. Most rear bars, especially aftermarket, trap air. So the air under the car, and all obviously, on the other side of the tyre, actually comes up here and gets trapped in the rear bar. If you just get rid of that rear bar, all of that turbulent air can now get out. So essentially, no rear bar on a lot of cars means you don't trap as much air under the back and therefore have less drag. Let's have a look at Jet 200. We basically drew a line as high as we could on the back and just cut everything off below it, and we just have a flat panel here. That's it. There's nowhere in the rear section where we can catch air, which acts like a parachute, which is drag. Now, in open class, we can't have a flat floor, so we just didn't bother trying to make a diffuser work. We added these vertical strakes to Jet 200 for two reasons. One, cosmetically it made the car look better, but secondly, we're just trying to manage the airflow that comes from behind the tyre that's probably a little bit more turbulent than what's on the inside of the tyre, and just try and keep those two sections of airflow a little bit separate. So we're just trying to manage the turbulent air as opposed to trying to create any downforce with what we've done at the back here. But just think of it this way, the easier it is for the air to get out from under the car is the less drag you have, and it also helps move the low pressure further back as well. So we're just trying to minimize drag as opposed to create any downforce with this design on the car. But the other thing is, and we'll draw it on the board here, if you've cut this section out and you hang a rear diffuser, you can hang the rear diffuser lower down and effectively try and give it some clean airflow under the car. But to be honest with you, it's just so hard to know with a car if there is any smooth airflow under there. You could go get it CFD designed by someone like Andrew Brilliant, Or you might even just do some good old-fashioned tough wool testing by just having little bits of string wool attached under the car to try and look and see if there is any smooth airflow under the back of the car. But to be honest, a rear diffuser without a flat floor is trying to ice skate uphill, as my mate Blade once said in a really old movie. And it's a tough thing to do. So diffusers look good, don't work 99% of the time when you put them on the car aftermarket. So in summary, what does all of this mean in the real world? Because I could get way more in depth than this and start doing calculations and get Andrew Brilliant to show some CFD, but we could be here for hundreds of thousands of hours talking about aero. But realistically, aero is such a big topic because it's different for every car. But Andrew Brilliant has developed what's called best practices, which is something that will just work for downforce but won't be optimized for drag, because that's really what aero is. You're trying to balance downforce, drag, and the performance of the car itself and make it all work together in a package. How can you guys learn from that in sort of a general enthusiast term? Well, let's look at a drag car or a top speed car first. In a drag car or a top speed car, all you care about is how fast you go. So you want to go as slippery through the air as possible. Like we've said so many times, any turbulent air, anywhere where the air detaches away from the surface of the car and becomes turbulent, is creating drag. It's exactly what it's doing. Detached air, turbulent air is drag. So if you want to go faster top speed or accelerate better, you want to make the car as smooth as possible. How can you do that? Well, eliminate anything that pokes out of the car. Take your side view mirrors off. Take your rear bar off, or trim the bottom of the rear bar so it can't catch any air. Modify the back of your wheel arches at the front to let air out. Put a negative pressure duct in the bonnet to let the air out. Block up any holes in the front bar that you don't need. To be honest, for drag racing and top speed, you're not going to need as much cooling as you do driving around. You could block off the side vents on your front bar, you could block off your brake ducts, you could block off your center grille, you can block off half your radiator. Like, there's so many things you could block off in most cars when you want to do top speed or drag racing. All of those things combined could give you 2, 3, 4, 5 kilometers per hour. It's all relative to how much power you have. But I have seen cars that hit 290 k's an hour over 1,000 meters, come in and cover their front end with gaffer tape and seal everything up and take their side view mirrors off, do everything they can to make the car slippery, go back out and crack 300 k's an hour. Sometimes they don't though, because they might have heat soak or other factors, but that's one way that you can use aero to go faster. So drag racing and top speed is one end of the spectrum, and then time attack is the other end of the spectrum, where it's all about maximum downforce. Now, I said that turbulent air and detached air creates drag, but just huge amounts of downforce creates drag as well. Every time you have to move the air, you are creating some drag. Now you see as you go up through the classes from Club Sprint to Open to Pro Class, these wings just get bigger and bigger and bigger. Some of these cars are generating 2 ton of downforce, but they're also creating huge amounts of drag. Now the balancing act is, the more drag you have means the more power you need to push the car through the air. But at the same time, more downforce is going to give you more cornering. Which one's going to give you a faster lap time? Well, it's a balancing act. So an example I'll use with balancing aero and performance is our car Jet 200. The very first time we did World Time Attack in 2011, we basically had no aero. In fact, the front end used to lift as it went down the straight. It was pretty cool. We went over 260 kilometers per hour with only like 370 kilowatts at the wheels. The car was slippery, didn't have a lot of drag or downforce, and it did a 1 minute 39. The following year we went back, I did some sort of basic aero stuff that I thought would work. We went 2 seconds faster with another 20 kilowatts, but our top speed actually went down. It was only like 259 k's an hour. We had a year off in 2013. We came back in 2014 with this aero package from Andrew Brilliant's advice, and Chris from CS Engineering and I did all this. And we went 2 seconds faster again, did a minute 35, but we had more power, but our top speed was massively reduced. In fact, our top speed barely nudged 250 k's an hour down the front straight. So we'd lost probably 20 k's an hour because we had extra power, but we still were nearly 20 k's an hour slower down the front straight, but we were 2 seconds faster. Now, the following year, we came back with a couple of slight revisions to the aero, a little bit more power, so we got our top speed up a little bit again, but we went 2 seconds faster again, probably more than anything because of the sequential gearbox. So it just goes to show that even though our power was going up over the 4 times we competed at World Time Attack, our top speed actually came down, but we went faster. So the downforce and the lower top speed and the better cornering was worth more to our lap time than just top speed down the straights. But but every car's a little bit different. I've watched some of the big horsepower GTRs take some downforce out of their car because they want to be super slippery for down the big straights and use the power to their advantage. So, and that's the thing about this topic of aero. It's just a never-ending refinement, development, studying. There's so much to it. But I just hope you guys have learnt the basics of it and some things that you might better do to your car. And obviously some myths have been dispelled here. Raising the bonnet at the back doesn't work. Rear diffusers that you buy for your car won't work. And obviously things like wing extensions and rocket dancers and things like that, they'll just ruin how your wing works. So yeah, there's a lot to it, but we hope you've learned something.